What does a homunculus represent in the brain? And is there one or many homunculus, or the plural form homunculi in the brain? Did you know that your brain has a map of your body? To understand where this map comes from, we need to go back to the year 1937, when two neurologists named Wilder Pinfield and Edwin Baldry were studying the brain. They operated on people's brains while the patients were awake. Sounds scary. But they were given local anesthesia, which blocks the pain in a specific body part during medical procedures. So, Pinfield gently stimulated tiny parts of the cerebral cortex or the outer layer of the brain with a small electrical current. When he did this, he asked patients questions like, "Did you feel something?" or "Did something move?" For example, a patient might say, "My hand moved," or "I felt a tingling in my face." After many surgeries, Pinfield had detailed notes about which brain area caused movement or sensation and in which body parts. Edwin Baldry then took these notes along with photographs and drawings and turned them into about 170 summary maps. From these maps, they measured three things. First, how much brain area was linked to each body part. Second, how many stimulation points were found in front and behind a large brain fold called the central sulcus. Third, how far each body part's representation stretched along this fold. Using all this information, they created a distorted drawing of a human body. This drawing was called the Homunculus, Latin for little man. Later, based on Pinfield's data, a 3D figure that visualized these maps was created. The homunculus does not show real body size. Instead, it shows how much brain space is devoted to each body part. Body parts that need very precise movement or sensation, like the hands, lips, and tongue, take up more space in the brain and appear very large. Body parts that need less precision appear much smaller. Pinfield's homunculus became extremely famous and appeared in many neuroscience textbooks. But later scientists re-examined Pinfield's original homunculus and pointed out key problems. They explained that the original homunculus mixed motor and sensory information into a single figure. This made the picture confusing. You could not tell which responses were motor and which were sensory, whether responses were on one side of the body or both, or whether different body parts overlapped in the brain. However, years later, Pinfield and Rasmussen revised the homunculus, separating and slightly modifying the motor and sensory representations. The motor homunculus is shown on the right and the sensory on the left, with the 3D models also available in this figure. Critics also noted that while the homunculus looks precise, it's unclear how body part sizes were determined. Terms like vertical and perpendicular extent were never clearly defined. It is unclear whether the vertical meant distance along the brain surface, or dipped into the brain, or simply how many stimulation sites were found. Furthermore, they stressed that many stimulation sites activated more than one body part. This means the brain is not organized into clean, separated stripes, as the homunculus seems to suggest. Instead, brain representations overlap. In other words, the homunculus is a simplified and ambiguous picture, and not a precise map of the brain. This raised an important question. If the homunculus is oversimplified, what does the organization of the brain's body maps really look like? To answer this question, we first need to look at how multiple maps were discovered and what each does. As neuroscience advanced, researchers discovered that the brain contains many body maps, or homunculi, not just the two motor and sensory maps which were originally identified. In the primary somatosensory cortex, part of sensory cortex, also called as S1, scientists found 4 separate body maps, known as Area 3A, 3B, 1, and 2. Each of these areas contains its own complete representation of the body. This was demonstrated most clearly in the classic work by John Cass and colleagues in the late 1970s and early 1980s. What they found was striking. Neurons in each area respond to touch from specific body parts, but each area emphasizes different aspect of sensation. For example, area 3B is especially sensitive to fine touch on the skin. Area 3A is more related to signals from muscles and joints. Area 1 and 2 integrate touch with information about shape, size, and movement. So even within primary somatosensory cortex, the brain is already representing the body multiple times for different computational purposes. In the secondary somatosensory cortex, or S2, researchers found at least 2 additional body maps. This already means that touch alone is represented multiple times in the brain. The motor system follows the same rule. Instead of one simple motor map, there are multiple motor representations, each involved in different aspects of movement. This showed scientists that having many maps is a normal feature of the brain. Recently, this idea was pushed even further. In 2023, Gordon and colleagues published a large study using tens of thousands of brain scans. They discovered that the classic motor homunculus is actually interrupted by several regions. Surprisingly, these regions do not represent individual body parts. Instead, they are part of a network involved in planning, action, coordinating movement, and controlling the whole body behavior. The researchers called this network the Somatocognitive Action Network, or SCAN. This means the motor cortex is not just a map of muscles. It is a system that combines body control with decision-making and planning. Importantly, these findings were confirmed across more than 50,000 brain scans, showing that this organization is consistent across people. To conclude, the homunculus, a representation of how the brain maps the body, is not a single map. There are many homunculi which spread across sensory, motor, and visual system, and even these maps are embedded in larger networks that support action, not just body parts. And what makes it even more remarkable is that these maps are not fixed. They can reorganize throughout life in response to injury, changes in sensory input, learning new skills, or even shifts in attention, demonstrating the brain's remarkable plasticity. Despite major advances, we still don't fully understand how the brain integrates its many body maps into a unified sense of the body, how goals and intentions shape these maps, why they differ across individuals, and how plasticity is regulated over time. Regardless, the homunculus is still useful as a teaching tool. But today we understand that it is only a simplified metaphor for a much more complex brain.